Thank you very much. I'm very happy to be here. My focus is on UAV classification, but also recently branched out to scalability and efficiency. And I kind of relate here in this project. So UAVs are unmanned aerial vehicles that become increasingly important and used in the past 5-10 years. And with this increased and exponential use comes increased public and private interest security concerns, whether it be airports, public institutions like universities or stadiums, or even more relevant, warfare. So one of the fundamental challenges in this space is the modern detection methods, or just detection. It's kind of a binary classification, whereas modern methods kind of need to pivot towards classification, which demands answers, which also need more data. Which kind of brings us to the fundamental challenge, which is data scarcity. It's fundamental to the space. It's very, very, very difficult to collect more data as custom drones and consumer drones flood the market and make it increasingly difficult to record new samples. So this is from my lab's upcoming paper here, 4,500 seconds, which is small data training approaches for deep UAV audio classification. As was presented, I'm Andrew Berg. I'm an undergraduate at the College of Charleston, along with my co-authors, Dr. Zhang and Dr. Wang, who are my mentors. So this paper isn't so much about state-of-the-art performance, so much as it is scaling and looking at different frameworks and tools to address the small data problem, which is fundamental to the space. So in this presentation, we're going to firstly go through the introductions, kind of motivate this work and previous work in our lab, as well as the field. From there, we're going to look at where I started on this project and kind of the narrative arc of our initial experiments, as well as the methodology, which would be data augmentations and parameter efficient fine tuning, and kind of how that progressed through our attempts through this project, as well as taking the project out of a vacuum and comparing it to previous work from our lab, how that might generalize and some intuitions behind that. And then finally, we'll conclude, and I'll touch on future work, as well as future work, if I might. So, quick overview. Deep learning is very simply large neural networks. That's kind of what deep learning subset means versus machine learning, which is more statistical analysis, whereas deep learning neural. As far as audio classification goes, we have an input audio sample. So this is waveform. This is the standard format for audio. So you can see here, we have some amount of data set for audio, and then the model is able to train on that and then classify the drone. So this is kind of a toy example, but we'll see how this scales up. Previous work from my lab by Dr. Wang used a custom CNN, quite a simple CNN here, with 2 convolutional blocks, standard convolution block, just hash norm, max pooling, dense layer, the normal stuff, as well as introducing, more importantly, a custom UAV dataset of our own. This is closed source, unfortunately, but kind of addresses the lack of data in the field for our lab. You can see here the manufacturers are broken down inside the little circle there. So DJI, if you're familiar, is a really large consumer-grade Chinese manufacturer of drones. It's important to target different manufacturers as they have kind of the relevant audio signal to them. They have some similarities. This was about 5,000 seconds. It was an unbalanced data set and was 10 classes of data set. However, for this work, we decided to change the data set a little bit, working with a balanced data set, closing in on 4,500 seconds. That was the title of our paper, with 3 different manufacturers from Mattel, DJI, as well as a custom drone, which is pretty interesting, and that included. So for each class, there's 100 samples of audio content, as well as there being 5 seconds per sample per clip. So if I want to back up for a second and kind of look at modern methods in audio and image classification. So this is kind of an ongoing field. It's been going on for the past 20 years, especially since the AlexNet kind of boom of convolutional neural networks. This has been a increasingly pacing field. So most of the methodology used in modern work is with larger data sets, so the order of magnitude of millions. So a very popular data set, ImageNet, which is open source, boasts about 14 million labeled samples, as well as AudioSet, which is about 2 million, Coco, which is about 350,000, and then there's ours, which is 900 samples. So you can see the disparity already right here is that we're not working with a lot of data, so our methodology needs to adapt and change to what's being addressed. This is kind of where I come along in the project. I'm a student, so I kind of came up to Dr. Wong and told her my interest, and we got this started, which was pretty fun. So I was really interested in addressing this problem from new direction using the standard, or industry standard now, of transformers. If you don't know what transformers are, we were introduced rather in 2017 from the Attention is All You Need paper, which is now infamous or famous. And this architecture kind of breaks down what a transformer is. Maybe not so important for this project scope, but from a high level, it has an encoder decoder block, as well as some amount of tokenization, and it revolutionized natural language processing as we know it, working with, in that paper, English to German translation. However, we're not working with text in this project, we're using audio. So things have to change in our methodology, in our model. So there's kind of two parts to that. First is the input data and how that's being worked with, as well as the model architecture and how that breaks down the input. So very standard in deep learning and machine learning is feature extraction for audio. And this essentially takes the input audio of waveform and makes it into a more feature-dense package or tensor. So in this case, it's small spectrogram. There's different variants of this with LFCC, MFCC, you name it. This is just what we chose. And this is essentially mapping the time dimension against the frequency dimension, which allows the whatever model we choose to better understand what's going on. So as I mentioned, the modeling, the architecture needs to change as the input changes from the standard transformer text to audio. And some great work has been done at MIT addressing this with the audio spectrogram transformer, which is a novel architecture. I'm going to be referring to this for the remainder of the presentation as AST. Essentially what this does, it gets rid of the decoder block and replaces that with a classifier linear block, as well as an input layer which uses patchified splits of, I think for this one it was 16 by 16. You can kind of think of this as like a larger convolution with some maybe nuance in config. And this allows for state-of-the-art classification of audio set. However, one fundamental challenge of transformers that I noticed, and you'll probably notice as well if you ever work in this space, is they require more data. Their scale is built for larger scale systems, such as products like products like ChatGPT and Claude and Gemini. They're built for the massive scale of data. Because simply won't work for the 900 samples that we have in our data set. So what's the solution here? Well, one solution I propose is fine-tuning. And this is very simply taking a model that's already trained, in this case audio set, or the audio spectrogram transformer, and train it further on a smaller data set, which is our own. So the audio spectrogram transformer has about 86 million parameters. This is simply the scalars inside, the numbers inside of the model. And then we're going to train all of the parameters again on our smaller data set. So this is our first attempt, and it went as well as you would expect. Not very well. So we got about 45% validation accuracy, which is pretty disappointing. We're going to be using this graph format for the rest of the presentation, so get used to it. The x-axis is representing the number of trainable parameters as percent, so we'll see how that maps out in the coming slides. As well as our train validation split was 80-20 with 5-fold cross validation for robustness. So that didn't go very well, and we kind of had to pivot and think of other ideas and how to move this project along. And the second idea that I came up with was linear probing. And what linear probing is a ablation tactic to see if the model, the pre-trained knowledge, has any knowledge of what we're trying to train it on. So in this case, audio spectrograms, which makes sense. You might have maybe some, from a high level, like an abstract intuition of what this might be able to learn. So it's only training on less than 0.001% of the parameters, which is quite a disparity between the two. So if we see it maps out, it performed quite well. Talking out at about 88% validation accuracy, give or take 2%. So already we can see this big disparity between the full fine-tuning and the linear probing, where less than 0.001% of parameters is being trained, and it's performing better actually, whereas full fine-tuning is performing much worse. So at this point in the presentation, I think it's good to back up and kind of think about the problems from a higher level. So first of all, this is kind of fundamental, is the data scarcity problem, which is just not going to go away. We can record more samples, but it's just never going to match up to the modern data set size, especially as the drone field keeps manufacturing new drones. And the second is the negative correlation between parameters and the model performance, which I think is quite interesting. And we'll look at that further in a few slides. So very simply, to address data scarcity, we can use data augmentation. This is a tried and true practice in machine learning. For our purposes, we use relevant augmentations to the space, such as, from this paper, such as distortion, pitch shifting, and noise. You can see it's applied to the waveform rather than the spectrogram, just for consistency. And notably, this isn't replacing the samples, but it's inflating the data sets, the training set rather, to increase the data set quantity. This is done in kind of folds, so 0, 1, 3, and 5, which multiplies the training sets, and you can see they're grouped here. And here's the performance. So the max out of the different augmentation experiments were such. 0 augmentations didn't perform the augmentations didn't perform any better when you were probing, whereas there was a huge jump in performance of the max of the full fine-tuning with 5 augmentations, which is pretty interesting to see, again, the relationship with the negative correlates. So if we start thinking about further the inverse correlation between parameters and performance, it kind of naturally progresses to doing more with less, which is the idea of parameter efficient fine-tuning. So this is a pretty vast and growing field in deep learning, which addresses the efficiency gap. So say, for example, you're trying to fine-tune ChatGPT and you want to do it efficiently. It's pretty difficult without parameter efficient fine-tuning, which is simply using a small subset of selective parameters or additive parameters to train on the model, which allows you to either achieve the same results as full fine-tuning or even better. I'm not going to break down every type, but the ones we use in this paper are adapters, which add new feed-forward kind of networks on top of the frozen parameters, as well as addition-based and reparameterized, or LoRa. We'll get into that. So the 4 methods that we used were these 2 first. So we use LoRa, which stands for low-rank adaptation. And what this does is it freezes all of the original weights, all the pre-trained weights, and adds on top in parallel 2 new matrices, as well as dropout if you wanted, A and B. And these are defined simply as a Gaussian distribution, and instead of training the pre-trained weights, we're actually training the added LoRa weights. So they're also divided into ranks. So as a hyperparameter, you can change the relative rank, which is simply a feature of the dimensionality. So more rank, more dimensions, captures more of the training update. LoRa typically accounts for 1 to 2% of the total trainable parameters. And this, I think 2019 was when it was first introduced and kind of marked the shift in PNT. A newer, more recent adaptation of LoRa is AdaLoRa, which stands for Adaptive Low-Rank Adaptation, and this adds a E matrix, adds a third E matrix, which allows for, you guessed it, adaptive fine-tuning. This essentially looks at the gradient flow and gives each layer that's targeted an importance score, and as the importance score changes over training, so does the relative ranks of LoRa. So essentially, at a high level, this uses and is more efficient than LoRa in itself, as it changes the number of dimensions of the updated weights. So the next 2 methods we used were IA3 and OFT. So IA3 is kind of a mouthful. It stands for Infused Adapter by Inhibiting and Amplifying Interactivations. There's no need for it to be so complicated, but it's very simple. It simply scales the attention mechanism. So it adds learnable vectors. You can see here LV, LK, and LFF around the attention mechanism, whether it be by the ReLU or by the value. This is quite a simple idea. It simply scales what's already inside the attention mechanism while only learning or updating the gradients of these learnable vectors. And then lastly is OFT. And OFT stands for orthogonal fine-tuning, and this is the idea that most of the updates are performed on the orthogonal or diagonal weights. This is a pretty interesting idea. However, if you introduce it purely from theory, it doesn't pan out to be very efficient, as there's a lot of diagonal weights. So what the authors of OFT have done a bit of parameterization using Cayley parameterization and some different rescaling to make it much smaller and more efficient, accounting for about 1% of total model parameters. So all of these kind of, the technical implementation isn't maybe so important from a high level, but just know that they work with the parameters and interesting in different ways to do more with less, essentially. So as we look at the results, we can kind of see the groupings here. All the way on the left is the familiar linear probing, and then towards the center are the adapters, or the PFT methods, and then all the way to the right is full-time. So if we look at the best two results, we can see that OFT performed the absolute highest with 5 augmentations, absolutely crushing linear probing with 96% validation accuracy. Pretty interesting that we could achieve more with less, even despite the transformer not being, not wanting to work with smaller data. And if towards the center, I think generally it's about 1% of the total model trainable parameters, which is not very many at all. Another of note is Ada LoRa, which performs slightly less, but still quite well. And the groupings are quite interesting as well for the augmentations. And then all the way at the bottom is the LoRa method, which I didn't have high hopes for anyways, but performed less than 40%. These results don't exist in a vacuum though. We have to kind of compare it to our previous work of custom CNN of my mentor, Dr. Wong. I've updated this to use 3 convolutional blocks, not too important, and accounts for about 5 million parameters. So this is from scratch instead of being pre-trained. So all the model parameters are being trained in return. If we compare that to the groupings of the previous, we can see that the CNN actually just outright performs the best transformer run. And maybe I can speak to the intuition of why this is. So CNNs have an inductive bias towards image and audio classification. This is simply a result of how the operation was invented. And especially this, combined with a small data scale, it kind of turns the favor towards CNNs in general. So we're running short on time, but to conclude, we kind of went over the initial experiments in the transformer approach and kind of how that came to be, as well as 2 proposed solutions to working with the small data scale and why that matters to the data scarcity problem of UAV classification. So we went over data augmentations, maybe some relevant augmentations for that, as well as parameter efficient fine-tuning and how we can do more with less. And then we compared CNNs versus transformers and explained maybe some intuition. So as far as future works, this has actually already been done, but the whole point of the project is to scale up for our own lab and to kind of classify drones, maybe not just with audio, but also other modalities. But a very interesting problem here is scale. So in the future work, which was already under review, is for a larger data set, which is about 3 times the size. We're working with much different manufacturers, as well as using the pre-training fine-tuning paradigm, using ResNet and VIT. Oh yes, if I want to talk about, if I might, the future works after this has already been published, it will probably be about not just UAV classification, but also the generalization therein of larger models to smaller data, which has been quite promising. So all of the work is supported by the South Carolina Research Authority. We're very grateful, as well as all the code is open source. You can find it here if you're interested. And that's all I got. Thank you, guys.
Thank you very much. And as always, you can, yeah.
Yes.
Yeah, for me, I would like maybe to see like a big picture of how this would work at the end. So you use like the audio classifications. You have like, how would this be put to work at the end? And do you have like microphones running around?
Sure. So you mean like at applications level, like how it would be deployed? Yeah. Sure. So this is mostly working with the scale of data. So this is like early days, I'd say. But from like an inference perspective and deploying it in like on the ground, I would say there's definitely a limitation to audio, as audio can kind of be really noisy and stuff. I'd say this is a few years from being actually deployed, but in the real world system there would be different modalities such as like microphones, audio, cameras, as well as like radar systems.
Okay, so you would classify basically the drone that's trying to penetrate somewhere based on its audio profile, among other things.
Yes, so I would say if this were to be deployed in full application for, I don't know, protecting an airport, there's obviously planes that fly by which have a different signature than a drone. And maybe you're also keeping track of your own company's drones as well as intruder drones. You can kind of, perhaps at a high level, map it out and then see what kind of crosses and penetrates the line of where you don't want them to be.
For another question, for the audio data set that you use, you mentioned that it's somehow limited. but what I would find interesting is how you would deal with false positives, because I think in a very globalized supply chain, and if a drone manufacturer would, like, the audio profile would depend on the rotor size and what kind of motor it's using and weight and so on and so forth. So how would this account for part sharing? So for example, VGI using or sourcing parts from another supplier that would sell probably to another drone manufacturer.
That's a great question. So this isn't fully addressed here. It's definitely a future work that just goes into applications level. Maybe this is the kind of touched on with like custom drones and how those play with off-the-shelf parts. But I would say this is like you can't always control what the enemy has versus what your company has. So I think the solution might be like a more robust classification system as a whole, using more than just audio, using maybe radar, mapping them out, as well as the visual to have a full integrated system. Any other questions? Please.
Does the CNN architecture have any major drawbacks, or what was the initial motivation to look at the transformer architecture as an alternative?
Yes, so I think I did a poor job kind of bringing this up in the presentation, but it's all about scale. So you kind of picture the small data works really well with CNN right now, but as we scale up to hundreds of thousands or thousands of classes, this will definitely change, as simply the scaling laws for transformers are much more ambitious than CNNs might be, which is kind of the whole revolution in AI. We can already see this in future works of like the larger CNNs that are pre-trained to perform better, and then AST like very close behind, and then as we maybe move to 100 classes, AST performing a bit better. That's kind of motivation to scale.
Okay. Is your institute also involved in locating the operator?
Yeah, so that would be, so there's a modality called radio frequency, which is, so if you imagine like a remote controller has like a link to the drum, the radio frequency you can kind of pick up on, I think 6,000 hertz is the right frequency. You can kind of see and map the maps. That's maybe a few years down the road for the project as a whole, but yes, you can do that in our institutions. Looking toward that. Good question. Thank you.
We have like for one more, yeah?
I have one question.
Please.
Did you showed us a slide where you state augmentation for the full training of the transformer model, and did you adjust the training epochs accordingly, or did you always use the same epochs, the models epochs?
The model epochs, you're saying?
So like, how many epochs did you train?
Yeah, so that was, there was early stopping involved. I kind of brushed over the technical just to have a high level. But I'd say it's about 30 epochs, pretty short, with early stopping and monitoring of the loss curve, which also will show.
Okay.
Yeah.
Okay, so then,
I think we're good.
yeah, I think if no one has anything, I mean, if it's super short, we would have time for it, but if no one has something, then, yes, thank you very much again.